Hello class, welcome back. This tutorial will introduce how to build the linear regression models in R and also how to build the regression trees. So we will first use a new dataset, insurance dataset. Let's first import this dataset in R and check the structure of this dataset. So in total, we have 7 different variables and 1,338 different observations. Those observations are patients. So we have 3 different factor variables, and age is the patient's age, and gender, then BMI index, the number of children they have, if he or she is a smoker, and the region he or she lives. And the target variable, the dependent variable, is expenses, which is our dependent variable. And we will first build a simple linear regression. So what is a simple linear regression? Simple linear regression is using one independent variable to compose a linear regression. So y equals to alpha plus beta times x. And how can we get those value beta and alpha? We will use these two functions first. And how can we implement these two functions in R? Let's check. So we will first calculate the covariance of so in our case, we want to build a simple linear regression with expenses as dependent variable and variable age as independent variable, which age is the predictor and expenses is the target variable. So we will first calculate the covariance of these two variables and then divide it by the variance of age. And then we will calculate the alpha. So alpha equals to the mean of y, which is the expenses, minus this beta times the average of x. So the average of x is average of age. So we will use this mean function to calculate the average value of both expenses and the age. So let's run this chunk, see the values are. So we will calculate the beta equals to 257.7 and the alpha equals to 3,165.885. And next, we want to calculate the correlation between these expenses and age variables. We will both use definition and function. So by using definition, the correlation of x and y equals to the covariance of x and y divided by standard deviation x times standard deviation y. And the covariance of xy is a measure of how much two variables change together, while the formula used to calculate covariance is using the expected value function. Well, but in R, we already have the covariance function, so here we will use the covariance function to calculate this expenses and age, and then divide it by the multiplication of expenses of the standard deviation value of the expenses and age. Well, besides using the definition, we can also use the existing correlation function. So let's check if the values are the same. So remember, what we said, the correlation, if the range of the correlation is from -1 to 1, and if the correlation is close to 1, means these two variables has like a very strong like positive correlation. While if they're close to -1, it has like negative correlation, strong negative correlation. But if they're close to 0, means they have like little or no correlation. So here we see the correlation between expenses and age is positive, but it's not close to 1, means they don't have a strong positive correlation. Well, you can visualize the correlation between expenses and age using scalar plot or using this function pairs. So basically here is the graph plot we get. Well, you can see, well, they certainly do have like a positive correlation, but the correlation is not very like strong. Well, next we want to calculate the slope of this straight line. So as you can see, when we build a simple linear regression, we actually compose a straight line, and the slope of this straight line we want to calculate using the correlation coefficient. Well, by definition, using the slope, we will use the correlation between the x and y times the division between the standard deviation of y and standard deviation of x. And as you can see that the slope of this straight line is actually the beta coefficient. So let's check and see if these two values are the same. So these two values are the same. Which means the slope of this straight line is actually the beta coefficient for the variable age. And besides building like calculate this alpha coefficient and beta coefficient bar manually using functions by definition, we can use a linear regression model like embedded in R. So let's see if we calculate the coefficient correctly. So this Lm is a function we're going to use to build this linear regression, and the expenses is our dependent variable, and age is our only independent variable, and we use the data in. Well, let's first check this simple linear regression. So it will return me two coefficients value. First one is for the intersection, and next one is for the age. So the first one is actually the value for alpha coefficient, and this one is for the beta coefficient. So let's check the summary of this model. So besides those two coefficients, we have more values presented here. We will have residuals, and we'll also have the t-values and the p-values, the r-square and adjust r-square. So the p-values is actually the probability of incorrectly reject the hypothesis. Well, the non-hypothesis is we assume the beta coefficient equals to 0, and the r square is actually the square of the correlation between this y and x, and this value represents how fit this model is for this data set, and like how much variance this model can explain for this data set. Well, as you can see, we'll not only use only one, right, the age variable. So this r-square is pretty low, it's less than 10%. And see here we have another r-square called adjusted r-square. Well, adjusted r-square is nothing but the change of R squared that adjusts the number of terms in a model. So it adjusts this R squared value by using the number of predictor and also the total sample size. In this case, the value will not keep increasing when we have more predictors. Next, we will build multiple linear regressions models. We will first create a regression function. So basically, multiple linear regression model means we will now have more than one predictors. So we will define a function called regression, and this function needs two parameters, y and x. While inside this function, we include them with this braces, and we first transform this x into a matrix and add an additional column index into this matrix. And then we use this solve function. T is get the matrix the transpose of a matrix, and solve is get the inverse of a matrix. And see here we got this percentage sign times the percentage sign. This is for the multiplication for matrix. And B is the beta coefficient for each one of the predictors. Well, how can we use this function, this formula, to calculate the beta coefficients? So let's see. Well, initially this one is what we want to build. The y is our target variable. We have d different n different predictors, and we want to get the minimal value for this square, which means, well, this one yi is the actual target variable values, and this part is the predicted variable, a predicted value. So we want to get the minimum value for the square of the differences between the prediction and the actual values. So we will get the derivation for variable beta. So now we will have this function. So actually this one is the implementation for the function we just showed you. Well, after we get the column B, which is the values for the beta coefficients for each one of the predictors in this multiple linear regression, we'll give a name estimate for this column and also print this B. Well, we will test this regression function using simple linear regression. So now we only use the age as our predictor. And let's see if we have the correct regression function. So see here we have the same values as we had before using linear model function. So which means we have the correct regression function. Well, let's use the regression function with multiple predictors. Well, we'll only use the age, BMI, children, which are the three numeric variables to create this linear regression first. Well, these are some approaches to exclude the factor variables. Remember, we have three factor variables. So we'll use this regression model to compose a linear multiple regression model using these three numeric variables. So let's check. So the intercept, which is the alpha, and the rest three values are for the beta coefficient values for the three predictors respectively. And let's check if we can get the same values, same beta and alpha coefficients values using this linear model function. So similarly, we will use age, BMI, and number of children as our predictors. And data is also insurance data. So let's build this model and check the model. So you can see basically we have the same values, which means we have the correct regression function. Next, let's check the summary of this multiple regression model. So, well, we can see here we have 3 variables, and the p-values for these 3 predictors are all less than 0.05, which means like at a significant level 0.05, they're all significantly affect the target variable expenses. And remember, when we only use like one variable age, one predictor age, the variance that explained by the age is only 0.08, which is almost 8% of the variance. Well, we increased to 12%. Well, when we calculate just R squared, which means just adjusted the predictor numbers, we got like 11% of the just R squared. Next, we will use this multiple linear regression to do the prediction for the medical expenses and also to explain some of the dependent variable, the predictors. Well, we will first explore and prepare the data for further partition. So we can check the summary for this target variable expenses and also see the histogram of this variable. Well, next the one of our factor variable is region. Let's check. It includes 4 levels: northeast, northwest, southeast, southwest. And we can also explore the correlation between the 4 different numeric variables that our dataset has. So let's use this correlation to check the correlation coefficients of the 3 numeric variables with our target variable expenses. So our age variable has the highest correlation coefficients, while the rest of them, such as the children, well, the correlation coefficients is close to 0, which means they have little correlations. And well, you can also visualize the correlations using the pairs function. Well, sometimes if you have this error, means the plot window is too small. You need to make it larger to present your plot. And so here's our plots. Well, next we want to build a base explanatory model on the whole datasets using all the predictors. So besides expenses, we include the rest 6 different predictors, and the dataset is a whole dataset. We haven't partitioned the dataset yet. Well, you can also, besides using this add sign to like combine all these predictors, you can also use this dot to represent all the 6 predictors except these expenses. So let's build this model and check the coefficients and the summaries. Well, similarly, we have those beta coefficients values. Well, one thing to note is that we have 6 predictors, right? But now we have 8 different beta coefficients. Well, see here. Remember, we have a variable predictor code sex and predictor code smoker and a predictor code region. These 3 are the factor variable or the categorical variable that in our dataset. Well, the LM function, the linear model function, will automatically transform those categorical variables into dummy variables, which give them value 0 and 1. So, for instance, we have the sex variable, right, before originally, and now we have a sex male, which means this one is a dummy variable for the sex variables. So, for example, if the value in the sex variable is male, we will give them a value 1 in this sex male variable, and a value 0 if it's a female in the sex variable. So similarly, the smoker yes, which means if the value in the original smoker variable is yes, this smoker yes equals to 1, otherwise equals to 0. Well, because region variables has 4 different levels, so well, we now have northwest, southeast, and southwest. So this northwest, the reference class level is northeast. So if it is northwest, it will give a value 1, and if it's northeast, it will give a value 0, and so on. Well, let's see. So the age, the beta coefficient for a variable age is a positive value, and it's 257, almost 57. So it means if this patient increase his or her age by 1, he will keep other, like the rest of variables, unchanged. The medical expenses will increase by $257, and so it's similarly, if this patient had 1 more children, and keep other like variables unchanged, the medical expenses will increase by $475.7. Well, one thing also to note is we are assuming those independent variables, those predictors are independent with the errors. And well, let's check one factor variable. So this sex male means comparing to the female, the male will reduce the medical expenses by $131.3. For this region northwest, it means comparing to the patient lives in the region northeast, the people in the region northwest will reduce the medical expenses by $352.8. And we can see that the sex male and region northwest are two variables, two predictors are not without the star, which means they're not significant affect the medical expenses. Well, let's also see the R squared. Well, with 1, 2, 3, 4, 6. So with 6 different predictors, we can explain the variance using our model by 75%, almost 75% by just R squared. We will partition our insurance dataset into training and testing and build a base predictive model and evaluate prediction performance. Well, so firstly, we will partition our dataset into training and testing. We will use 50% of instances to compose our training dataset, and the rest of 50, we further partition them into test 1 and test 2. So in total, 25% of the instances will belong to test 1, and the rest 25 will belong to test 2. And then we will build this linear regression model based on our training dataset. And let's build this model together. So you can see that based on this training dataset, the almost 76% of the variance has been explained, and we have age, BMI, number of children, and smoker as our significant predictors. Well, next we will predict the expenses for the patients in both testing 1, testing 2 datasets. We will use this model and the testing 1, testing 2 datasets. Well, next we want to evaluate prediction based on some evaluation metrics. Well, we can no longer use the accuracy, precision, recall, F measure, and so on, because we have the target variable is a continuous variable, which is not a categorical variable. So we need some new measures to evaluate the prediction performance. So we will still use the M matrix, but now we change the name of the measures to MAE, RMSE, MAPE, RMSPE, RRSE, RAE, correlation, R square. So those are the error measures. So those are function how to calculate those errors. So the mean absolute error, root mean squared error, and so on. So we include these 6 different error measures together with the correlation and R squared to evaluate how the performance of this model built on the training dataset to predict the house cost, house expenses for both testing 1, testing 2 datasets. So let's run these 3 lines. So these are the errors we calculate, and let's check the correlation between the prediction and the actual medical expenses. So for the test data 1, we have the correlation value reaches 85%, and for testing data 2, similar, almost 86%. While for the R square, we have the almost 73% of variance has been explained in the testing data 1 by this model, while almost 74% of the variance has been explained in the testing data 2. Well, next, similar to the tutorial we had last week, we will generate randomly sampled training and testing pairs, while still to get the average performance for these linear regression models. So similarly, we set n equals 3, so we'll build 3 different linear regression models using 3 iterations, and then get the average performance for these 3 models. So here we use this insurance linear total results as an array to append the evaluation result from each iteration, and use this row means to get the average performance. So let's run this whole chunk and see. Well, for the randomly sampled pairs, we use 66% of the instances to compose the training dataset, and the rest 34% will be the testing datasets. So let's see. Yeah, the correlation is higher, which means the average correlation between prediction and actual medical expenses is 87%, which is pretty good, and the R square is around 76%, which is also not bad. Well, next we will partition the insurance dataset in a new way and then do some further predictions. Well, we will partition 70% of the instance will belong to the training dataset, and the rest 30% will belong to the testing dataset. And then we still build this model, linear regression model using the training dataset. And let's build the model together. And well, let's check the differences between the model built on the training dataset and the built on the whole dataset. So you can see the values for the beta coefficients are similar. Well, the values are a little bit different, but the direction of impact are the same. For example, age is positively influence the health care expenses, and also this one, age is also positively influence the healthcare costs. And the p-value are a little different. So we now have the model built on the training dataset, and we want to predict the health expenses on both training and testing dataset. Well, if we build a model on training dataset and then we test this model on training dataset, we always face a problem of overfitting. So let's see if we have this problem. And let's predict using this training set model, predict the healthcare costs based on both training and testing dataset. And we calculate the correlation between the actual value of expenses with the prediction. So you can see here the correlation for the prediction on the testing dataset is better than the correlation on training dataset, which means we don't have this overfitting problem, because the performance on testing datasets are even better than the performance on training dataset. Well, next we will use different error measures to evaluate the performance of this small linear regression model. So besides using the M-metric function and specify the error names in the function, we can also define our functions, define those error functions ourselves. For example, we can use this function and by definition to create this equation to calculate the mean absolute error and also to calculate the root mean squared error. And let's check the performance by these two errors. So you can see this is the mean absolute error by the performance on the testing dataset, and this is on the training dataset. So in terms of the mean absolute error, like the performance on the training dataset is better than the performance on the testing dataset. Well, but in terms of the root mean squared error, the performance on the testing dataset is better than the performance on the training dataset. But you can see those numbers are similar, like they have no big differences. So we can know that the performance on both training and dataset are similar, have no big differences. Well, next we can use this M-metric function to just generate all the error measures and correlation and R-squared. So those are like two different approaches. You can define your measures yourself, or you can just use this M-metric to output you with the measures. So basically, the prediction performance on the training dataset, even though this model is built on the training dataset, the performance such as R-squared, correlation are worse than the testing dataset, the performance on the testing dataset. But in terms of some error measures, for example, the MAE, MAPE, and RMSPE, the error measures are less than the error that generated on the testing datasets. Well, next we will try to improve the linear regression model by introducing new predictors and some interactions of the predictors. So first of all, we will introduce two new predictors. The first one is H2. H2 is using the values from variable age and square the values from the predictor age. And next one is PMI 30. Well, PMI 30 is a dummy variable, so if the original PMI predictor, the value inside PMI predictor is larger than 30, we give this PMI 30 value 1, but if it's less than 30, we'll give it 0. So this is how we create a dummy variable using if-else function. Well, next we will, because now we have new additional variables in our insurance dataset, we will further partition this new insurance dataset, still using 70% and 30% partition. And we will build 3 different improved explanatory model using the training dataset. Well, see here, the first improved model, we introduce a new predictor, which is the interaction between BMI 30, which is our new variable, new predictor, the dummy variable, times the smoker. Well, in the second improved model, we only introduce the H2. And the third model, we not only introduce H2, we also include these interactions, interaction predictor. Well, let's check the performance of these 3 improved models. So let's only look at R-squared now. You can look at other evaluations later. So for the third improved model, we can reach a R-squared more than 86%. Well, for the model 2, we still got the R-squared didn't change much. It's 75%. And for the model 1, we have, yes, also 86%. Well, next we will use this improved model to predict the healthcare expenses using both training and testing dataset. So we will demonstrate you by using the improved training model 3, which is our last improved model. And we use the testing dataset first to see the prediction. And then we will still use all these error measures and correlation R-squared to check the evaluated performance. So you can see for the testing dataset, we reached R-squared 87%, and the correlation between this prediction and actual cost or actual expenses is pretty high. It's over 90%, which means they have really strong positive correlation. And next, we will also generate prediction on the training dataset with this third improved trained model. And let's see the performance. Well, the performance a little, in terms of correlation R-squared, the performance is a little worse because the values of R-squared and correlations are less than those ones generated from the testing dataset. But in terms of the errors, some of them are less than errors from the previous performance, which means in this case they're better. So next we will use regression tree we'll build a regression tree for our insurance dataset. Well, regression tree is similar to decision tree. However, one big difference is, well, the target variable for regression tree is numeric variable, and the criteria for deciding which which splitting point to use is called standard deviation reduction. So let's first giving an example of how to calculate the standard deviation reduction. So this set include all these values, all these numbers, and we have two different splitting point options. First one is splitting point A, which split between this 5 and 6. The second one is splitting point B, which split from this between this 4 and 5. Well, we will compute the standard deviation reduction respectively and compare their values. The larger the standard deviation reduction, the better. So here is the equation of how to calculate this standard deviation reduction. We implement this equation to R using this standard deviation function and length, and then we calculate these two standard deviation reduction and then compare their values. So in our case, splitting point B has the reduction value 1.4, and splitting point A only has the value 1.2. So in this case, we will choose splitting point B over splitting point A. Well, next we will use this insurance dataset to build the regression tree models. Well, we'll first need to load this rpart library, and then use this rpart function to build a regression tree model. So the data we use is still the training dataset, and we use all the variables as predictors. And let's check the basic information of this tree. So you can see that while the training dataset has 938 instances, so at its root it has 938 instances. While the first split is smoker, so about 750 patients are in non-smoker category, and 188 are in the smoker category. Well, if there is a star, which means this is a leaf of this tree. So basically, the target variable, medical expenses, which is a continuous variable, has been categorized, which means now it only has 1, 2, 3, 4, 5 different values. So if a patient who is not a smoker and his age is less than 46.5, well, the medical expense for him is this $5,871.387. So let's further check the summary of this model. We will get more detailed information of this tree. Well, it will give me the detailed information for every node. So for example, node number 1, which is the root, and node number 2, 4, 5, 3, 6, 7, 14, and 15. Those all present to you. Well, they will calculate the mean, the error, and the left sum, the right sum, and the splits, and the improvement at each split. So let's visualize this tree by using the rpart plot function. Well, you need to first install and load this rpart.plot library. So here we got this tree. Remember, we have 5 different leaves. So now those 5 different leaves are listed here. So if this patient is not a smoker, and if his BMI is, if his if this patient is not a smoker, so this is equals to yes, we'll go to this split, this set. So if this is not a smoker and his age is less than 46.5, the healthcare expenses will be 5,871. Well, next we'll do some adjustment to this diagram. So we add for 3 additional parameters: fallen leaves equals to true, type, and extra. Well, fallen leaves will make sure the leaves will fall into the bottom of this diagram, and type and extra will affect the way the decision and nodes are labeled in the leaf. So let's run this one. So you can see all the leaves fall into the bottom. So still we got the healthcare costs for the patients on the first row of the leaf, while on the second row we have n equals to, I think it's for, I don't know why it's so blurry, but yeah, the number of instances that fall into the sleeve is 481, and the percentage is 51.25%. Well, this is the regression tree we built, and we want to evaluate this regression tree using the testing and also the training data set. So we first generate prediction for the health expenses for both training and testing data set. And let's check the summary. For the predictions and actual values. So they look, the differences are not, for the minimum, the prediction for the minimum is almost 5,071, while for the actual expenses it's 1,141. Well, because you know that even using this R-part decision tree, we not only have 5 values for the health expenses. So all these instances will have one of these values. So the minimum value will be this 5,871. So let's now see the correlation between these two, between the prediction and the actual value. The correlation actually is pretty high, means they're moving together, change together. And well, we also tested on the training data set, and let's see the correlation. Well, the correlation is also pretty high, similar to the performance on the testing data set. And then we generate prediction performance in measurement using the R-minor packages, including all the error measures for both training and testing datasets. Well, you can see the R-square, the values for both testing and training datasets are similar, like 83%, which means 83% of errors have been explained by this model in both training and testing dataset. Well, in terms of the errors, I see no big differences between these two datasets. Well, we want to improve this model. We want to improve this regression tree model by using a new function called M5P. Well, M5P is also a regression tree model, but what's different is, remember here we have 5 distinct values for all the instances. And but for the M5P model, it will generate another linear model regression on each leaf of this regression tree. So let's see. Well, this function is inside our Weka library, so we need to first load this our Weka library, and then we build this model using also training dataset. So now we have our M5 model ready. Let's check this model first. So you can see that, well, instead of the exact specific expenses number, now we have the 4 different linear regression model on the leaf nodes. So let's go through one condition first. So the smoker equals to yes. Well, this is the dummy variable, remember we had before. If this equals to 0, it means this is not a smoker. If this value equals to the value of this smoker equals to yes, equals to 1 means this patient is a smoker. So now the condition is if this smoker equals to yes, this variable is less or equal to 0.5, which means if this patient is a non-smoker, we'll go, well, here, if the age of this patient is larger than 42.5, we will compute the medical expenses using linear regression model 2. Okay, similarly, let's check the summary of this model. Well, it will show you the performance of this model performed on the training dataset. So now we have the correlation coefficient, the mean absolute error, and other errors, and so on. So now we already have this M5 regression tree model built on the training dataset. We want to predict and evaluate the performance using both training and testing dataset. Well, let's predict the health expenses using both training and testing dataset. And then let's check the correlation between the predicted value and the true values. So you can see that both of them are like pretty high. Well, we can also use the M metric to generate all these error measures to evaluate the prediction. Now here we'll only evaluate them based on the testing dataset. And besides M metric function, because we use our Weka library, we can also use the evaluate Weka classifier function to both do the prediction and the evaluation at the same time. So let's see. Well, we can see that it will present us with the correlation coefficient, the mean absolute error, root mean squared error, and so on. Well, basically, that's all we will include in this tutorial. Well, in the next tutorial, we'll change the dataset to white wine dataset and also build regression tree and linear regression models. See you. Bye.